6.3 Simple Machines. How do you move something that is too heavy to carry? How did the ancients, Egyptians, build the pyramids long before the inventions of powered machines? The answer to these questions has to do with the use of simple machines. In this section, you will learn how simple machines multiply forces to accomplish many tasks. Machines allow us to do incredible things, moving huge steel beams, digging tunnels that connect two islands, and building 100-story skyscrapers are examples. What makes these things possible? Have we developed superpowers since the days of our ancestors? In a way, we have developed superpowers. Our powers come from the clever human inventions of machines. A machine is a device like a bicycle with moving parts that work together to accomplish a task. Figure 611. All the parts of the bicycle work together to transform forces from your muscles into motion. A bicycle allows you to travel at faster speeds and for far greater distances than you could on foot. Machines are designed to do something. To understand how a machine works, think about input and output. The input includes everything you do to make the machine work, like pushing on the bicycle pads. The output is what the machine does for you, like going fast or climbing a steep hill. For the machines in this chapter, the input and output may be force, power, or energy. The development of cars, airplanes, and other modern machines began with the invention of simple machines. A simple machine, such as a lever, is an unpowered mechanical device that accomplishes a task with only one movement. A lever allows you to move a rock that weighs 10 times or more what you weigh, figure 612. Some important types of machines are shown below. Simple machines work with forces. The input force is the force you apply to the machine. The output force is the force the machine applies to what you are trying to move. Figure 612 shows how a lever is arranged to create a large output force from a small input force. A rope and pulley system is a simple machine made by connecting a rope to one or more pulleys. You apply the input force to the rope, and the output force is applied to the load you are lifting. One person could easily lift an elephant with a properly designed system of ropes and pulleys, figure 613. Most of the machines we use today are made up of a combination of different types of simple machines. For example, the bicycle uses wheels and axles, levers, the pedals and the kickstand, and gears. If you take apart a complex machine such as a video cassette recorder, a clock, or a car engine, you will find many simple machines inside. The machine does work because it applies a force over a distance. If you are using the machine, you also do work because you apply force to the machine to make it move. By definition, a simple machine has no source of energy except the immediate forces you apply. That means the only way to get output work from a simple machine is to do input work on the machine. In fact, the output work done by the simple machine can never exceed the input work done on the machine. In a perfect machine, the output work exactly equals the input work. Of course, there is no perfect machine. Friction always converts some of the input work to heat and wear, so the output work is always less than the input work. However, for a well-designed machine, friction can be minimal, and we can often assume input and output work are approximately equal. Figure 6.4 shows a perfect machine that lifts a 10 Newton weight a distance of 0.5 meters. The machine does output work of 5 joules, 10 times 0.5. How much input work must be supplied? The simple machine has been designed to multiply the force. Notice that the input work is only 5 newtons. This means the input distance must be 1 meter because 5 times 1 is 5 joules. You must do 5 joules of input work to get 5 joules of output work. Since the input force is half, you have to apply the input force for twice the distance. The output work of a machine can never be greater than the input work. This is a rule that is true for all machines. When you design a machine that multiplies force, you pay by having to apply the force over a greater distance. Machines and efficiency. The efficiency of a machine is the ratio of work output to work input. Efficiency is usually expressed in percent. A perfect machine has an efficiency of 100%. That means that the output work exactly equals the input work. No energy is diverted by friction or other factors. Because some friction is always present, perfect machines are impossible. The bicycle is one of the most efficient machines ever made. A good bicycle can convert 95% of the input work of your muscles into output work or motion. You calculate efficiency by dividing the output work by the input work. A machine that is 75% efficient can produce 3 joules of output work for every 4 joules of input work, figure 615. That means 1 joule out of every 4 is lost to friction. In real machines, the output work is less than the input work because of friction. When analyzing a machine, it helps to think about like the diagram at the left. The input work is divided between output work and losses due to friction. You can see that cars are not very efficient at using the energy in gasoline. Only 13% of the energy in a gallon of gas is transferred into output work. Engineers are constantly working to improve the efficiency of cars. An important way to increase the efficiency of a machine is to reduce the friction. Ball bearings and oils reduce rolling friction. Slippery materials such as Teflon reduce sliding friction. Designing a car with a streamlined shape helps reduce air friction. All these techniques are increasing efficiency. Advantage in levers. You can make a lever by balancing a board on a log, figure 616. Pushing down on one end of the board lifts a load on the other end of the board. The downward force you apply is the input force. The upward force that the board exerts on the rock is the output force. All levers include a stiff structure that rotates around a fixed point called the fulcrum. The side of the lever where the input force is applied is called the input arm. The output arm is the end of the lever that applies the output force. Levers are useful because you can arrange the fulcrum in the input and output arms to make the output force much larger than the input force. Mechanical advantage is the ratio of output force divided by input force. If a machine has a mechanical advantage of 2, then the output force is 2 times the input force. When the fulcrum is at the center, the input and output forces are equal. The mechanical advantage is 1. The input and output forces are different if the fulcrum is not in the center. The side of the lever with the longer arm has the smaller force. If the output force arm is 3 times longer than the output arm, the output force is 3 times greater than the input force. This lever has a mechanical advantage of 3. Levers are found in many common machines. Pliers, a wheelbarrow, and even your arm work as levers. Levers are classified as one of 3 types, or classes, defined by the location of the input and output force relative to the fulcrum. First class, second class, and third class levers. And strings carry tension forces along their length. The tension is the same at every point in a rope. If a rope is not moving, the tension is equal to the force pulling on each end below. Ropes or strings do not carry pushing forces. Figure 618 shows 3 different configurations of ropes and pulleys. Imagine pulling with an input force of 5 newtons. In case A, the load feels a force equal to your input force. In case B, there are 2 strands of rope supporting the load, so the load feels 2 times your input force. In case C, there are 3 strands, so the output force is 3 times your input force. The mechanical advantage of a pulley system depends on the number of strands of rope directly supporting the load. In case C, 3 strands directly support the load, so the output force is 3 times the input force. The mechanical advantage is 3. To make a rope and pulley system with a greater mechanical advantage, you can increase the number of strands directly supporting the load by using more pulleys. To raise the load 1 meter in case C, the input end of the rope must be pulled for 3 meters. This is because each of the 3 supporting strands must shorten by 1 meter. The mechanical advantage is 3, but the input force must be applied for 3 times the distance as the output force. This is another example of the rule stating that output and input work are equal for a perfect machine. Ramps and screws. Machines that rotate often use gears, figure 619. Machines such as small drills require small forces at high speeds. Other machines, such as the paddle wheel on the back of a steamboat, require large forces at low speed. Gears allow rotating speeds to change while power stays constant. The rule for how 2 gears turn depends on the number of teeth on each. Gear teeth don't slip. Moving 36 teeth on one gear means that 36 teeth also move on any connected gear. Consider a 36-tooth gear connected to a 12-tooth gear. The 12-tooth gear must turn 3 times. 3 times 12 equals 36 for every turn of the 36-tooth gear, figure 619. A ramp allows you to raise a heavy cart with less force than you would need to lift it straight up. Ramps reduce the input force by increasing the distance over which the input force acts. For example, suppose a 10-meter ramp is used to lift a car. 1 meter. The input distance is 10 times the output distance. If the ramp were frictionless, the input force would therefore be 1/10 the output force. Screw is a simple machine that turns rotating motion into linear motion. A screw works like a ramp that curves as it gets higher. The ramp on a screw is called a thread. Imagine unwrapping one turn of a thread to make a straight ramp. Each turn of a screw advances the nut the same distance it would have gone sliding up the ramp. The lead of the screw is the distance it advances in one turn. A screw with a lead of 1.2 millimeters advances 1.2 millimeters for every turn. Stop here and answer these questions.